I'm going to run through a fairly large selection of questions quite quickly, all at the high school level to undergraduate university. So for the first question, just ask, what is the molar mass of air? So on the right here I have a periodic table, and the next few questions are all going to be about molar masses. So for this first question, so the molar mass of air, I wouldn't say is a quantity I would quote all the time, but we can define a average molar mass for air. And so the average molar mass for air would just be the constituent atoms of air and then the molar mass of each of those constituents. So air is roughly 78.1% nitrogen, 21% oxygen, and then roughly 0.9% argon. And so if we sum up each of the constituent atoms with their proper percentages, then we would get an average molar mass for air. So with that in mind, just gonna that. So as I said, the average molar mass for air should then be 78.1% times the molar mass for nitrogen plus 0.21% times the molar mass for oxygen plus 0.9% for the molar mass for argon. The molar mass for nitrogen would just be 2 times the molar mass of a nitrogen atom, which I'm just going to use as 14.01. So just the 2 significant digits, or 2 decimal places. That would be 4 significant digits. Molar mass for oxygen will just be 2 times that of an individual atom, which if you look in the periodic table, you'll see it's 16, or roughly. And if we look up the molar mass for argon, then it would be 2 times, then it's not 2 of them. The molar mass for argon just comes out to be 39.95. So we can start to replace these. And so this would be 32 and 39. Okay. Now, if we just run through this quick addition problem, then this would just be 21.884, keeping extra digits just for rounding error. Sum it all up, and we get roughly 28.96 grams per mole. So the average molar mass for air is roughly 28.96. Okay, if we look at the solution here, it's basically what they went through. They only used oxygen and nitrogen, and so then their average molar mass comes out to be a little less, but obviously it just depends on your assumptions. So the solution is correct. Okay. Okay, so this one is again just a simple molar mass question. So I just asked, what is the molar mass of aluminum? So all you're going to do to find the molar mass of an element is locate it on the table. Okay, so aluminum is right there. And of course, if you could see that close, but that's just going to be a tiny little blurry number there. But if you look on a periodic table with actual legible numbers, you would see that the molar mass for aluminum is 26.9815 grams per mole. Okay, and so it's all about just locating it on the table. And again, so yes, over here, it's basically what's said. Actually, I want to stay there. So for this next one, it's just what is the molar mass of sulfuric acid. So for sulfuric acid, we have H2SO4. So we need hydrogen, sulfur, and oxygen. So the molar mass of hydrogen, and this is going to depend, the number you get in the end is going to depend on the number of digits you keep, but I'm just going to use 1.01, 16.00 for oxygen, and 32.06 for sulfur. Okay, so just grab a new whiteboard here. So H2SO4, so our molar mass for H2SO4 is going to be 2 times the molar mass of hydrogen plus the molar mass of sulfur plus 4 times the molar mass for oxygen, right? Because we have 2 hydrogens, 1 sulfur, and 4 oxygens. So that's 2 times 1.01 grams per mole plus 32.06 grams per mole plus 4 times 16 grams per mole. And so that's just 2.02 plus 32 plus 64. And then if we sum those all up, we'll find that the, I'm going to space this out a bit better. If we sum these all up, we find that the molar mass for H2SO4 is just 98 0.08 grams per mole. Checking the solution here. So they just used an extra digit on each of their molar masses. So again, your answer is going to depend on how many figures you keep and how many you use in the beginning, but it's still just the same basically. So that looks good. Okay, so for the next one here, just what's the molar mass of water? So for water, we're going to use hydrogen and oxygen, right? Because water is H2O. And so again, I'm going to use 1.01 for hydrogen, and I'm going to use 16 for oxygen. Oops. Okay. And I'll just grab a new one. So this is the fourth one. I haven't really been numbering, but so for the molar mass of water, we have 1.01, and oxygen is 16. So then the molar mass of H2O is just 2 times that of hydrogen plus that for oxygen. Which comes out to be 2.02. Just putting everything out. And so our final answer is just that the molar mass of water is 18.02 grams per mole. Now if we check our solution here, they used quite a few digits in their molar masses, so their final answer comes out to be 18.015. Obviously, if you round it to 2 decimal places, they would be the same. So that looks good. And okay, so for the next one here, what is the molar mass of sodium hydroxide? So sodium hydroxide is just NaOH. Okay, so we're going to need oxygen, hydrogen, and sodium, which is over here. So the if we could see the numbers, or if you look closely at your own periodic table, you should find that the mass of hydrogen is roughly 1.01. Mass of oxygen is roughly 16. I'll put these units in here. And the molar mass for sodium is 22.99. Okay, and I'm just going to grab a new sheet. So if we're looking for the molar mass of sodium hydroxide, that's just going to be the molar mass for sodium plus the molar mass for oxygen plus the molar mass for hydrogen, as there's just one sodium, one oxygen, one hydrogen. And so that's 22.99 grams per mole plus 16 grams per mole plus 1.01 grams per mole. So summing these all up, we see that the molar mass for sodium hydroxide is 40. And again, depending on units, you might get a different answer. So they only used 1 decimal place on those two and 2 on hydrogen, giving them 40.01, but it still looks good. And correct, okay. And now for, I believe, my final mass question. It asks, what is the mass of an oxygen atom? So this is now not molar mass, but just mass of one atom. And so we locate oxygen, and the molar mass of oxygen is, we're going to use 16 grams per mole. I'm just going to grab a new sheet. So the molar mass of oxygen is 16. Now, to get the mass of one atom, what we have to use is that 1 mole of atoms is the Avogadro's number of atoms, or molecules, I should say. In this case, we're talking about atoms, but if we were talking about molecules, then it would be molecules. Okay, so 1 mole is roughly 6.022 10 to the 23 atoms. Okay, so what that means is that we can divide by this value, or if we rearrange this short equation here, we see that 1 is equal to 1 mole over the Avogadro's number of atoms, and you can always multiply something by 1, so we're going to go ahead and multiply our molar mass for oxygen by 1 and get 16.00 grams per mole times 1 mole over Avogadro's number. And the moles will cancel. And then if we take 16 and divide by 6.022 times 10 to the 23, we get a mass for an oxygen atom of 2.657 times 10 to the minus 23 grams per atom. Okay, so the mass of a single oxygen atom is 2.657 times 10 to the minus 23 grams. Okay, which is essentially what's followed here, just different number of decimal places, but that's fine. Solution is correct. There we go. Okay. All right, so that's going to be it for my molar mass questions. So this one asks, what is a homogeneous mixture? So a homogeneous mixture is one where you have a mixture of 2 or more substances in solution. Okay, so you've got 2 or more substances in your solution, or your solid phase, or your gas phase. So it all has to be single phase. and they're distributed equally throughout. So, it has no discoloration at any point, and it isn't in some strange concentration in one area. So any salt solution forms a homogeneous mixture with water. So any or sugar, air. Should put a number on this guy. Air is a homogeneous mixture of nitrogen, oxygen, and argon, and some trace gases. In homogeneous mixtures would include things like milk, which is a mixture of fat and water, which is why when you buy milk, you buy it homogenized, meaning it's been slurified until it's homogeneous. Right? So we have two phases here which are separated normally, and then if you blender it really fast, then you can get those two phases to get pushed together until you homogenize. And that's okay. Until you homogenize the milk. Also, lots of solids are inhomogeneous. There's plenty of minerals that if you look in one location or another, it'll be different than another area. In which the composition and appearance is uniform, and all in a single phase. Yeah, so it looks good. I just added a couple little things there, but nothing important. And we're just gonna back out. Actually, I'll go back to this. So what are the representative elements? So those are just, if we look at our periodic table, just the ones in S&P. Oops. So just the ones in the S&P block are usually considered the representative elements. And usually when I'm talking about main group elements, really just talking about the top few. But it technically includes the whole block. But of these main group elements, the top few are the most abundant, would have been the first to be discovered, and would have been the starter to the periodic table as we see it today. All of these elements behave fairly well, except for maybe hydrogen, but so lithium down all tend to form +1 charge quite readily. All the halogens love being -1 charge. The noble gases, at least until you get down into the D block, tend to be just completely filled valence and don't like to bond, so they tend to just stick to themselves. Oxygen and sulfur are fairly well behaved, tend to form -2 charges, and carbon and silicon are basically act similar, but of course carbon has become the base of all life for a reason, because it's much more abundant. Yeah, so that's essentially what are the representative elements, or what I would consider are the representative elements. Okay, so which is largely what's given here. Yeah, so basically the S and the P block. Looks good. Okay, so this one's just a simple conversion. So whenever you convert, in this case we're just doing milliliters to liters, but whenever you convert is sometimes handy. Well, obviously you need to remember how much of each substance, or how the quantities relate to each other, but I always find it helpful to use the equation that relates them. So if 1 liter is 1,000 mils, then that means 1 liter over 1,000 mils is equal to 1. And you can always multiply a quantity by 1. That means that you can always multiply something by this without changing anything. And so if you have a quantity like 26 milliliters and you want to convert it to liters, then you could just multiply it by 1, which is the same thing as multiplying it by 1 liter over 1,000 mils. And then your mils will cancel, and you would get 26 times 10 to the minus 3 liters. Obviously, there's a few easy or simple ways to skip some steps here, right? Because you could just add on the times 10 to the minus 3, but you'd have to remember that it's 10 to the minus 3. But I find if you can keep track of the relation between them and remember that this is how these conversion factors are made, that it's almost impossible to go wrong. Okay, and this solution is correct, which just gives the conversion of milliliters to liter is by multiplying by this factor, which is the one we have here. Okay, I'm just gonna grab a new one. So this asks, how much does 1 gallon of water weigh? So 1 gallon of water is 3.78541 liters, and I'm kind of realizing it's likely not visible. I'm just gonna go 1 gallon is 3.78541 liters. All right. Now the density of water, so the answer to this question depends on your density. So the density of water is 1 at about 4 degrees Celsius. And your density for water is 0.998 grams per mil. Now, obviously, with the number of digits I have there, they're actually the same number, but a little lower at 20 degrees. So depending on what temperature your gallon's at, you're going to get a slightly different mass. So if we use the 20 degrees Celsius value, then density is a mass over a volume. A gallon is a unit of volume, right, because it's in liters. So that means that our mass is our density times our volume, right? And so this will be, our mass is going to be 0.998 grams per mil times 3.78541 liters. And then using the conversion factor for liters to mils, which is 1 liter over 1,000 mils. But the other direction, so we need 1,000 mils over 1 liter, as we need the liters to cancel. And so running through this multiplication, 1,000 times this times 0.998, then our mass comes out to be 3.779 times 10 to the 3 grams, which is the same as 3.78 kilograms. Okay, so if we look at the solution given, so it's how much does 1 gallon of water weigh? The solution is 1 gallon of water weighs about 3.78 kilograms at room temperature, so that would be 20 degrees Celsius. So I'd say the solution is correct. But more work can be shown here. So this is just basically just the answer. But it's correct. Okay. For the next one here, what is a supersaturated solution? So before we get into what a supersaturated solution is, what is a saturated solution? So if we look at a substance's solubility, it's always given with respect to a liquid. So if we look at a very common substance, just salt, then we would find that the solubility of salt at 20 degrees Celsius, so it depends on temperature, so our solubility is 35.89 grams per 100 mil. I know what I was doing there. 35.89 grams per 100 mils. That means if we had 38 grams of NaCl in 100 mils of water, we would have a 35.89 grams per 100 mil saltwater solution, and we would still have we'd have a 35.89 grams per 100 mil saturated solution. So this would be saturated because we have the most salt in it we could possibly dissolve, and then we would still have about 2.11 grams of NaCl in the bottom of the glass. So there would still just be floating salt because this solution is completely saturated and we can no longer dissolve any more salt. Now if we look, then we would find that the solubility for NaCl is 38.47 grams per mil at 90 degrees Celsius. So what that means is if we take this exact solution, if we take this exact saltwater solution, if we take this exact saltwater solution and we heat it up to 90 degrees Celsius, then now we can get it all in there. So we would have now a solution of 38.00 grams per 100 mil saltwater solution at 90 degrees Celsius, because it will completely dissolve and it's not saturated because we haven't even hit the limit. Now what happens if we decrease the temperature? Well, if we decrease the temperature with our 38 gram per 100 ml saltwater solution, all of a sudden now, if we decrease the temperature back down to 20 degrees Celsius, say, then at least momentarily, depending on how fast we're able to lower our temperature, but at least for a bit, we would still have a 38 gram per 100 ml saltwater solution, which is over the saturation limit at that temperature and is therefore a supersaturated solution. And so, just to answer the question, a supersaturated solution is one where the concentration of solute is higher than the saturation limit, or higher than its solubility at that temperature. And the typical way to make them is as I've sketched out here, which is to heat the liquid until you can dissolve more than you would be able to at 20 degrees, and then quickly cool the solution. And it doesn't take very long, but it eventually crystallizes out, as some of us may be aware from some of those little science kits and stuff. So the answer here is a supersaturated solution is a solution that has more solute at a given temperature than is needed to form a saturated solution. So you're past your saturation limit or your solubility for the solute in the liquid. So that looks good. Okay. I'll just go here. All right. So this question states, at 100 degrees Celsius, the vapor pressure for water is 760 torr. The vapor pressure for methanol is 2625 torr, and the vapor pressure for ethanol is 1694 torr. Okay, and then which compound has the highest normal boiling point and which the lowest? Boiling is defined as the temperature which the vapor pressure meets the atmospheric pressure, right? So you want the vapor pressure to equal your atmospheric pressure. Atmospheric pressure, depending on where you live, obviously, is 760 torr. That's in those units, or it's 1 atmosphere, or it's 101.325 kilopascals, depending on the unit you're using. In this question, obviously, we're using torr, so we'll just stick to torr. So a substance can heat up until the vapor pressure reaches the atmospheric pressure, after which it can readily just evolve out of the liquid and into the gas phase. So if we look at these substances here, right, water has just boiled at 100 degrees Celsius, which isn't surprising. Methanol has likely been boiling for a long time, and ethanol as well. So if we want the highest boiling point, and the assumption here, and I think it's valid, is that your vapor pressure at this should just increase at a fairly quick rate, but increase constantly over the temperature range. So there's no kinks in it. There's no reason to assume that at a lower temperature the ordering of any of these compounds would change. So we would assume that the highest boiling point is the substance with the lowest VP, or vapor pressure, and we would assume that the lowest boiling point, and I probably should just write that in, is with the highest VP, right? And so the lowest vapor pressure is water, and the highest vapor pressure is methanol, right? So that means that water would have the highest boiling point, and it means that methanol would have the lowest boiling point. Right. So that's, again, just assuming that the vapor pressure just follows a functional form and there's no kind of swapping in between. Okay, so looking at the answer here, the boiling point is defined at the temperature at which the vapor pressure of the liquid equals the atmospheric pressure. And they're directly proportional, or inversely proportional, I suppose. So yeah. So the boiling point of water is, okay, so yeah, so that's just okay, so if we look, the water is just boiled, so methanol and ethanol have been boiling for a while, so the highest boiling point would be water, and methanol would have the lowest boiling point. Yep, okay. Looks good. Okay, so we're looking for, in this one, we're looking for the electron configuration for iron. So I'm actually just going to grab this out again just quickly, and I'm going to erase this stuff. Okay, so for electron configurations, we just need to find where the element is and fill up our orbitals, right? And recall that this is the S block, and the periodic table helps us remember that each S orbital can only hold 2 electrons, right? There's only 2 elements in each of the S blocks, so they can only hold 2. The P block is over here, and 1, 2, 3, 4, 5, 6 can only hold 6, and the D block is in here, and there's 10 of those. So the D block can only hold 10, the S block can only hold 2, and the P block can only hold 6. As far as getting up to here, it's fairly straightforward, right? So we start at the top here, and we would have 1s2, and we just can count along until we reach iron, basically. So from this block, we're going to have 2s2, and then 2p. I'm just going to write them down. Of course, we're not going to get up to 4p. And over here we have the 1s's, the 2s's, and the 3s's. So we've got 2s, and we're going to fill that, and then we're going to go up to 2p, and we're going to fill that because iron is way past there. And then we've got 3s, and then 3p, and then 4s, and then 3d. Okay, so and then the D block. So the D block is numbered 1 less than what it's in. So this is the 4p. This is the 4s, right? But this here is the 3d. Now it seems confusing, but I'm going to talk about a little bit why that is and how it's actually quite helpful in a second. So in the 3D block we have 1, 2, 3, 4, 5, 6. So it's going to be 3d6. Now the reason why it's quite helpful that it's named 3D is that this is actually incorrect, because the way we draw the electron configurations is usually energetically. So we'd want to have the 3D first, like that. And so then this would be the electron configuration for iron. And yeah. And so it's, you just run through each of the blocks and keep going up and filling in with your electrons. So first we need to find it on the periodic table, which is what we did. And it has to have the correct number of electrons. And so then you get this configuration, which is what we have here. So the solution looks correct to me. And I'm just going to say solution is correct. And okay. And then for my final question here, I'm going to run through a few Lewis structures. So the first one here is a Lewis structure for methanol. So this is, I think, my 13th. Okay, so methanol is CH3OH. to do Lewis structures, you just need to recall the electron configurations, specifically the valences. So hydrogen just has one electron, and we represented it as a dot. Carbon has one s electrons, but we don't consider those, and instead we're just talking about the valence, which is the outer shell. So then carbon's valence is just 4 electrons, and oxygen again would be, the valence would just be 2s2, 2p4, so it has 6. We represent it like this, where we pair up we get 4 in, and then we pair them up as we go. And I've placed them on opposite side, as that is the typical way. For the most part, paired electrons want to be as far away from each other as possible. Obviously, this is kind of a sketching algorithm rather than an actual, this is what the structure looks like, but still we try to make it as lifelike as possible. So for methanol, we're just going to put these components that I've sketched out here into place. So we've got H, C, H, O, and then H. And then we just join up the dots that are next to each other, as those will become the bonding electrons. And then we have our Lewis structure for methanol, right, where we've bound these guys, and then we have our lone pair of electrons on our 2 lone pairs on oxygen. Okay. I'm going to just make a new one for vinyl chloride. So vinyl chloride is H2C, CHCl, and then we just need to identify our components. So hydrogen has a single electron, carbon has its 4 valence electrons, and chlorine has 7. But because most of them are paired, it essentially acts like a hydrogen, as it only has the 1 unpaired electron. And then again, we can pile these up around our center, around our atoms. With our appropriate dots. Join our bonding electrons. Now we're given here that there's a double bond there, so that means 2 of those are going to join. And as this kind of looks funny, we might want to redraw it as it typically is seen, which is just like this. But leaving in all of our lone pairs. So that's really what differentiates chlorine from hydrogen, is, well, besides the mass difference, but those lone pairs. Okay, and then for the last one here, I'm going to go through acetonitrile, or acrylonitrile. Okay, so again, identify our components. So the hydrogen and carbon are the same, but in this case now nitrogen has 5 valence electrons, meaning it has 1 lone pair and then 3 left for bonding. And so we've got H, C, H, and just filling these in basically as they come up in the equation. Okay, and then so here we've got these bonding, these would have to bond, that bonds, and then we've got 3 on the end here, so they must all be bonding. And again, I'm just redrawing this so that it looks slightly more like what we'd expect. And not forgetting the lone pairs. And so then that would be acrylonitrile. Now going back down through the solutions given, we see that this is the methanol structure I came up with. That's the vinyl chloride solution, or vinyl chloride structure I came up with, and then the acrylonitrile, all with their lone pairs all shown, so this solution is correct. And that's it. And then, okay, so that's all the questions for today that I'm going to run through. If you enjoyed this, please subscribe, and if you'd like to submit your own questions, please visit the OneClass site. This has been Jeff Krause for OneClass, and I will see you again.